So this is the instruction video or recording for this project in this unit. And I'm going to start with Google. Somehow, oh, here it shows, celebrating Hank Adams, apparently today as I'm recording this. We need two pieces of software. I don't know what that means there. And both of them are very unique. So when I type in PHET, I come up with it right away. There it is. PHET or PHET simulations. All sims. Notice they don't necessarily just cover physics, but chemistry, math, earth science, biology. Quite a few. Originally it's called physics, educational technology, but as I said, it's more than just physics. So here we go. And yeah, there are 110 results here. And I'm going to look for the one with the pendulum, which, if I paid attention, and oh, there it is. Oh, was it right in front of me? Anyway, there it is. Okay, there we go. Nothing to download, by the way. I'm just doing this all online here. Here, once I'm in the Pendulum lab, I really don't understand much of a difference between these three here, but I did notice there's a slight difference here when I click on lab, because it gives me this little period timer down here. And basically we're going to look at letting a pendulum swing and measuring its period, and its period, you can see that in a moment here, is once, forth, and back. So left to right and back, or from the middle left all the way to the right, and then back to the middle. There we go. So that's what we're going to look at. We're going to do 10 measurements, starting with 10 centimeters here, 0.10 meters, very short, and then we're going to go all the way up to 1.00. The only adjustment I'm going to make on this entire page, after I've clicked already the period timer here, there it is that I'm going to change this one here to 9.82 meters per second squared. The gravity of 9.81 is just fine, or 9.80, but 9.82, actually, that's it in Alaska. So I might as well use this one here, as most students are from Alaska. And that is actually gravity. What it means, 9.82 meters per second squared, is that is how fast an object is accelerating when you drop it. And the same thing then goes for the pendulum, because technically it's dropping on a string, right? All right, I'm going to make a short break here, and a short pause for myself. And I'm returning. I think I'm going to stop this here for now. And actually I will reset it. In order to analyze the data that we're going to get very shortly, I need a software in order to analyze those data, and that is Desmos. And again, this is also very unique. So when I type in Desmos, it's usually the very first link that comes up. There it is. And just like the other one, there's nothing to download, there's nothing to log in. I could get an account. You don't have to do that. The only advantage of an account would be that you could save your things in some kind of folder, but you can even do that even without it. All right, let's go. So these are the two things that we're going to need. I'm going to go back over here to the. I'm going to make this a little smaller here so I can see what I'm clicking on up here. All right, I'm going to start with my first data point. I'm going to pull, so I have 0.10 meters. I'm going to get the period timer here, and I'm only going to let it swing very, very small angles. I'm going to click the period timer, 0.6346. And I'm going to enter these two numbers here, 0.10 and the 0.6346, into Desmos. And Desmos is very user-friendly. I need to put these numbers in a table, and I tell Desmos table, and there it is. My X is the 0.10, and my Y is the 0.6346 seconds. And there's the data point. I'm going to go back, change this one here to Okay, actually not this way. Shift the one over there, and then it goes 10 centimeters up. Again, small angles only. This only works for small angles very well. And here we go, 0.8976. Okay, there we go. I can already do something here. Notice when I click on Zoom Fit. Oh, there it is. And then I can use my wheel on the mouse to zoom out a little bit. Go back here. This here to 0.30 meters. And there we go, 1.0993. .0993, I believe it was. I'm going to double check that. Yep. Okay. Okay, at this point, I want to start modeling these data. So I'm going to put an equation in here. But before I do that, I'm just going to show a keyboard here. These are the symbols I need. On the very left on your keyboard, you find this tilde symbol, which I use for proportional to, which actually it's decimals that is using it, proportional to instead of an equal sign. So that's why we need the tilde, and then up here we need this caret symbol, soon, which means to the power of something. So for example, to the second power, which would be squared, or the third power, which would be cubed. So we will need that very soon here. And then I'm also going to use this little asterisk here, which is a times. So just wanting to point out there will be a few symbols that we need. All right, so here we go. I'm going to model these data, and again, Desmos is very user-friendly. So I'm going to type in Y1. Notice what it did with the 1 right away. It put it as a subscript there, just like it says in the table. Proportional to, that's the tilde. And it looks kind of like a line. And then from previous math classes, you know, y equals mx plus b. So that's exactly what I'm going to do. M, which is the slope, times x, but it ought to be x1. There we go. Again, I put it as subscript right away. So times x1 plus b, which would be the y-intercept. That looks actually pretty good. I'm going to change a couple of things here. I'm going to hold this down while I click on it. There we go. It gives me different colors. I'm going to choose the same color here. And here I'm also going to hold this one down. And usually I do like these dots here, but I'm going to use these open circles here, and I'm going to make these a little bigger. For example, 11. Yep, there we go. And actually, that doesn't look too bad. Oh yeah, and then I can use that little plus here for the zoom fit, and again, zoom out a little bit. There we go. That's good. All right, next data point. Uh, 1.2693. 1.2693. Did I get that right? 2693, is that what I did? Yeah. I have a very bad short-term memory. So here we go up here. I believe that this fat simulation is also very intuitive, very easy to handle. So there we go. Oops, try it again. There we go. I don't even have to ever change the angle here. As I said, just very small angles. 1.4191. There we go. And here we go. Oops. I have to click this one here. 1.5545. 1.5545. Okay, I'm going to click that little plus symbol there again. And that actually doesn't look too bad. However, there's something interesting coming up here, which is that these setup points in the middle are kind of lying above, and then you have one here and one over here. And these data that we get from this pendulum simulation are very perfect data. And so having this kind of go off the straight line is an indicator that a straight line just doesn't work. And so here comes a new thing in, a new curve. I'm going to go in here, and I'm going to use that caret symbol that I mentioned earlier. So here's that caret symbol, which doesn't show, but I just used it. And here I'm going to put, because I don't know if it's squared or cubed or whatever, I'm just going to put a variable there, n, for that. And ooh, notice that one here works really nicely. By the way, the n is this one down here, 0.49943. That will change, by the way, as we're putting more data, and you will see that. All right, a few more data here. .6790. Was it 1.6790? Is that what it was? I think so. Yep. Okay, just a few more. 1.7949. I should type this first. 1.7949 and 0.80. Still pretty good. I'm just moving this over here with the mouse. All right, a couple more. 1.9038. 9038. And that one is, ooh, no, I made a mistake. 1.9038. I just hit enter there, and that unfortunately moved the row down. Okay, I got rid of that one. All right, and the last measurement. 2.0067. Let's just stop this one here. 2.0067. 1.00. There we go. So here is the analysis of these data. It looks pretty good. All right, and this is actually exactly what I want you to do, what I showed you over the last 12 minutes. Use this one here, this Pendulum Lab applet from PHET, to collect the data. By the way, I forgot to shift the gravity earlier to 9.82. At some point, I guess I reset it, so it's 9.81. All right. And then to graph these data in Desmos. And if you want, you may actually use these data that I showed you here in my video. What you then have to submit is this particular Desmos link. And the way you get it is by clicking on this one here where it says Share Graph. And there it is. That would be yours then, the one that you use. Please don't use mine, okay? Do your own and, yeah, show me your data. It could be, again, your data or mine. I'm going to show you a little bit more here about what happened with this particular equation here. The whole thing is called a regression curve. And the regression curve is trying to model the data. And notice these are virtually perfect, right? In fact, this regression coefficient over here, the R squared, is what's called the regression coefficient. The closer it is to 1.0000, the better the data are. This one here says 1.0000, which means perfect data, which is no surprise because this particular applet here is very precise, so it works with virtually perfect data. All right, let me actually change one here. So for example, if I change this one here maybe to 1.7849, even that one still cut it. Let's try something else here, like a 5 there. There we go. Notice this. So if I have somewhat different here, and we can see it that this data point is off now. Now we're not getting this 1.000. Still very good data, right? It's very close to 1.00. But anyway, I believe that was at 1.7949. Okay, these other numbers here, they're part of the equation. So this here would be the 2.007. Looks like it ought to be rounded to 2. I'll show you that in a moment. And this one here, the 0.49963, well, that looks like the exponent should be, looks like it ought to be rounded to 0.5. And the last one here, the negative 0.0007 here, means that's possibly rounded to 0. By the way, that would be here where it goes to that 0 point. All right, so I'm going to use this canvas here to write on, and I hope my pen works today. So here's that equation that you see there. So y1 is proportional to m x1 to the n power. There's a times in between. And then there's a plus b. There we go. By the way, that little point that showed up there, that's my hand touching the screen. All right, so now I'm going to plug in the data. That is actually the results. I'm plugging in the results here that we have, the 2.007 and so on. And I'm going to use simply y equals something. And so m, let's round it to 2, times the x here. Sorry about my handwriting. To the power 0.49963. Let me round it to 0.5. And then minus the b here, which is minus 0.0007 and so on. And I will round that to 0, which means I'm simply going to erase that part. There we go. And I get rid of these little dots here. Okay. The 0.5 here that we see, I have to find my way back here. My writing marker. The 0.5 here that we see. Okay, I don't know. Okay, wait. Sorry about that. That wasn't my fault. I don't know how that happened here. I'll try this again. Again, the 0.5 is actually the square root. So 0.5 is the same as 1/2. And 1/2, you see that 2 there? When it's an exponent, it becomes, oops, and I think I have to shift this over here. When it's a power and exponent, it becomes the second root of something. That happens with the exponent. That's what the 0.5 means, and therefore I have the square root there. All right, and that's actually it. Again, telling you, collect the data with the PHET simulation for the pendulum. Again, nothing to log in. It should be quite intuitive. Or you can use the data that I presented here. Either way, if you collect your own data, make sure that you only have small angles here. All right. Use Desmos. Again, nothing to log in. It ought to be quite intuitive, user-friendly, the way you're using it. And then you click on here and share your Desmos link with me. And also write a brief comment on this particular project. And I'm really going to leave it open for this particular one. I make no restrictions on what kind of comment. And now I believe I'm finally done.